this first section is a quick review of what we had talked about during the last video. So our aim here is to review the naming of types 1, 2, and 3 compounds. So remember, the type 1 compounds were made of a metal and a nonmetal. That's one thing from the left side of the table, one thing from the right side of the table. And in this specific type of compound, we found that the metal only has one charge. So these are those things that we don't have to specify because we know where in the table they are labeled. And they are the first two columns. And then don't forget, we are adding zinc and silver to those two. The rules for naming type 1 compounds: the cation is named first and the anion is named second. Remember, the cation keeps its name, the anion keeps its root, but the ending is changed to IDE. An example formula might be something like NaCl, sodium chloride. So remember, we keep the cation name, the positive ion's name. The negative ion, we change the ending to IDE. Remember, this is one type of ionic compound. The second type of ionic compound is still made of a metal and a nonmetal. That's what makes it an ionic compound. But this time the metal can have multiple charges. So we're looking at those in the transition metal region of the periodic table, that 4 by 10 block in the center, with the addition of tin and lead. So remember, tin and lead, Sn and Pb, break that rule where they belong to the +4 -4 column. Instead, they behave more like the transition metals and they end up carrying multiple charges. Remember the rules for naming this type. It's still an ionic compound, but because it's type 2, we need to use Roman numerals, and that's because it can have multiple charges. So the charge isn't implied just by looking at the name. We have to use the name to infer the charge, and that charge is written in Roman numerals. The naming convention is the same. The cation is named first, anion is named second, and we use the root of the cation, put IDE on the anion, except in the middle, we have to use a Roman numeral. And remember, that Roman numeral represents the charge on the cation, not the anion. The anion will always have the same charge. In this specific type of compound, the charge on the cation can change, and therefore we need a way to represent that. Remember, we plug that Roman numeral right into the middle, right between the name of the cation and the anion. An example of this, Cr2O3. So if I give you the formula, you're able to give me the name. You know Cr, or you could look at Cr on the periodic table. That's chromium. O is oxygen, so that would be changed to oxide. I need to indicate the charge on the cation, but remember, first we need to find the charge on the cation. So in this case, we could look at it like a reverse crisscross. The 3 becomes the charge on chromium, the 2 becomes the charge on oxygen. Therefore, the name of this compound is chromium 3 oxide. Type 3 compounds are not ionic anymore. These are covalent compounds. So they're made of 2 nonmetals put together, or 2 elements from the right side only of that stair-stepper line on the periodic table. The rules for naming these compounds are to use prefixes. Remember, we have mono, di, tri, tetra, penta, hexa, and so on. These prefixes represent how many of each element are in this formula. And remember, we don't use mono for the first element, so something like CO2 would be called carbon dioxide, not monocarbon dioxide. We could put mono if there were only one of the second element, but in this case, there are 2 of the second element, which is where the di comes from. The subscripts indicate the charge on the element that that subscript is attached to. I would use these as examples, and since you have these already as examples in your notes and you can use your notes on the test, these are pretty clear examples that tell you how to name each type of compound. Remember, type 1 is ionic, type 2 is ionic. The only difference between these two is multiple charges versus only one charge. And then type 3 is what we would call covalent. And remember, it's called covalent because they're sharing their electrons. The electrons are found in their valence shell, so that's where the word covalent comes from. So this was just a quick review of naming different types of compounds. For section 5.5, our aim is to learn the names of common polyatomic ions and how to use them in naming compounds. So this is pretty similar to what we've been doing before. As far as naming goes, we're not learning any new naming rules. The methods we've used before will carry over into this section. The only thing that's changing are the names of the cations and anions. And in addition to that, coming up with the formula can sometimes be a little bit more difficult because we're dealing with polyatomics here. Now, the word polyatomic means many atom. Poly, many, atomic, atom. Therefore, we're dealing with a combination of atoms in one charged species. So normally on a test, I would give you a periodic table and I would have the polyatomic ions on the back. So this is not something that you would be required to remember unless you were going for the A-level test. And in that case, I would ask you to memorize the polyatomic ions. But we are going to talk about them. So remember, polyatomic ion is a charged group of many atoms. So this isn't just something like chlorine or oxygen where you would only see one atom. You're going to see a group of many different atoms that form a charge. So we can see here we have nitrate, nitrite, sulfate, sulfite, and so on. One of the things I want you to get out of this is the difference between ate and ite. Now, we can't make a simple rule like we can assign 4 oxygen to ite or 3 oxygen to ite because it's different depending on what compound that we're talking about. But what we can say is that ites have 1 less oxygen than ates. So remember, when we look at a formula, something like H2O, we can see that the 2 means we have 2 hydrogen, and the implied 1 next to oxygen means that there's only 1 oxygen present. So looking at nitrate, we can see that we have 3 oxygen. Looking at nitrite, we can see we have 2 oxygen. So ite has 1 less oxygen than ate in every case. Sulfate, 4 oxygen. Sulfite has 3 oxygen. Phosphate has 4. Phosphite has 3. Chlorate has 3. Chlorite has 2. Notice the charge is the same as long as the first element is the same. So when we have NO3, that's a -1 charge. NO2 still has a -1 charge. The only difference there is the number of oxygens that are present in the polyatomic. So again, there are a lot of different ways to remember these, and there are some mnemonics. If you look online, there's a lot of different methods for memorizing the polyatomics, but you have these on a sheet. If you didn't get one of those polyatomic ion sheets, if you didn't pick up the packet from the library, there is still a chem reference sheet in the Chapter 5 module on Canvas. So you can still access that, and on the back you will see that there are polyatomics. So you can have that with you on an exam. If I'm naming something like magnesium sulfate, remember I said the method for naming this is the same as it was before. So the first thing we have to ask ourselves, is it ionic? Yes, it's ionic because we have a metal for our cation. Remember, something that comes on the left side of the table, and we recognize that as magnesium. Sulfate is then our anion. So we should be able to recognize that sulfate is an anion. Therefore, since we have a cation and an anion, we have an ionic compound. So we follow ionic naming rules when we're naming this. So we have each of our species with their respective charges. So we know magnesium has a +2 charge, sulfate has a -2 charge. The important thing when dealing with the polyatomics is to keep the base of the polyatomic together. Before you do anything else, put parentheses around the base of your polyatomic. That's everything but the charge. When you get to the end, to the final answer, you'll be able to determine whether or not you need to keep these parentheses there. But they need to be there initially to remind yourself that this whole piece needs to stay together through this process. So what you want to do here is crisscross the charges. Again, the same way we would when coming up with the formula for an ionic compound. Just crisscross them. And when we do that, we can see that the 2 comes down to the base of magnesium, from sulfate, and the 2 that's at the top of magnesium comes down to the base of sulfate. If they're the same, remember what a formula tells you is ultimately the ratio of one to another. So again, looking at H2O, there's 2 hydrogen to every 1 oxygen. And if a formula tells us that ratio, we don't need to know that it's 2 to 2. We want that to be in the simplest form possible. And the simplest form possible is a 1 to 1 ratio. And remember, if there's 1, it's implied that there's 1 there just by writing the symbol. So we do not need to include the 1s. We also do not need parentheses in this case. Parentheses are only when there's going to be a subscript on the outside. So in this case, we do not need to put the parentheses there. So it's only necessary to write MgSO4. In our next example, sodium sulfate, we're going to take the same approach. We know sulfate is SO4 with a -2 charge. We know sodium is a type 1 cation, meaning we can get the charge from the periodic table. So we have sodium with a +1 charge and sulfate, SO4 with a -2 charge. Remember, we start by putting parentheses around the base of our polyatomic. And then when we do that, we carry them with us all the way to the end to see if we need them or not. So we crisscross. The 2 comes from the sulfate down to the base of sodium, and the 1 on sodium comes down to the base of sulfate. Do I need parentheses here? No, but I have to remember to take that 1 off first. Otherwise, we would get something like this. And this is telling me that I have 41 oxygen, and this is not the case. So I can take that 1 off because just by having what's there in parentheses, the 1 is implied anyway. I have at least 1 there if I write it down. So then my final answer is Na2SO4. Calcium hydroxide. We recognize again, calcium is a type 1 cation because it comes from one of those columns in the periodic table that I can identify by labeling the charge. So we know calcium has a +2 charge. Hydroxide was not in the list that I showed you, but it is on the list on your periodic table. Hydroxide has a -1 charge. Always put parentheses around the base of your polyatomic until you figure out if you need them or not. We do our crisscross, and we can see that we have calcium and then hydroxide with a 2 on the outside. Couple of things. 1, we can take off the 1 that's the subscript. 1s are never subscripts when they're by themselves. 2, do we need the parentheses here? Let's try writing this without parentheses and see if it means the same thing. Does that mean the same thing? No, it does not. The one on the left tells me that I have 2 of everything inside those parentheses, which means I have 2 oxygen and 2 hydrogen. The one on the right is telling me I have 2 hydrogen and just 1 oxygen. So this is not correct. I need the parentheses there because I need to represent that I have 2 of everything inside the parentheses. So the correct formula is Ca in parentheses OH and then a 2 on the outside of the parentheses. Ammonium sulfite. Ammonium is the only polyatomic cation. So we start with NH4 plus, which is ammonium, and then we're combining that with sulfite, which is SO3 with a -2 charge. So again, put parentheses around the base of your polyatomics in this case. We have 2 of them. Do your crisscross. We have NH4 in parentheses with a 2 on the outside and SO3 in parentheses with a 1 on the outside. Are both of these sets of parentheses needed? No, they're not. Anytime we have a 1 on the outside of parentheses, it is not required. Are the parentheses required around ammonium? Yes, because if I did not have the parentheses there, I would be writing NH42SO3. And this is not what I'm trying to convey. I need the parentheses there to show that I have 2 NH4 molecules and not 42 hydrogen atoms. There's a big difference between those two. So my final answer, no parentheses around SO3, no 1 around SO3 because it's implied that there's 1 just by being there, and then NH4 in parentheses with a 2 on the outside. Copper 2 sulfate. So this is a type 2 polyatomic compound. Copper 2, remember, means I am not able to identify the charge of copper by looking at the periodic table, so I need the name to tell me what the charge is. That's what the 2 means. So the 2 tells me I have a charge of positive 2 on copper. So I have copper with a positive 2 charge, and sulfate, and we know the formula for that is SO4 with a negative 2 charge. Parentheses around the SO4 to start with until we figure out if we need it or not. We do our crisscross, or without even doing the crisscross, you can see that this compound already has equal but opposite charges from its cation and anion. Therefore, we know the final ratio is going to be 1 to 1. So that means Cu2, SO4 in parentheses 2, or I can just cut straight to the final answer if I already see that 1 to 1 ratio and I have CuSO4. Now, going the other way, if I give you a formula and ask you to come up with the name, you're going to start by naming the cation, naming the anion, but the problem comes in recognizing the anion. So just like putting parentheses around the anion when you get started, it can be helpful that you identify where that anion exists in the formula before you get started. So this is why it can be helpful to learn your polyatomics, and not necessarily because memorization is required, but because it's easier to pick out quickly when you see something like this. So if you can recognize that NO3 is the base of nitrate, then it becomes easier when you're trying to name the compound. And then as far as silver, remember in the periodic table, we identified silver as being one of those elements that always had a set charge, even though it was in the middle of the transition elements. So we know that silver always has a charge of positive 1. So we have silver with a charge of positive 1, nitrate with a charge of negative 1. We can see that their charges are already in a 1 to 1 ratio. So that just means we take off those 1s. We don't have to name it like it's a type 2. We don't need a Roman numeral here. So instead of putting a Roman numeral, we know it's a type 1 cation. The name of this is just silver nitrate. I often see silver 1 nitrate. Remember, you only need that Roman numeral when you have a type 2 cation, when your cation can have more than one charge. That is not the case with silver. PbSO3 seems pretty straightforward. This one's tricky for a couple of different reasons. So the first thing we want to be able to do is list our cation and our anion. So we know our cation is lead, and we know that is Pb. And we know our anion is everything in parentheses, so that's SO3. So we want to figure out our charges. And remember, even though we were able to label the column of lead, we were also identifying that as something that we didn't know the charge. It wasn't set. So we know it can have multiple charges. So we have to figure out what that charge is. We can do the reverse crisscross if we want. We can bring the 2 back up to the top of lead and the implied 1 up to the top of SO3. So this means this becomes positive 2, SO3 becomes negative 1. However, this should flag you as kind of a problem. So what we see here is that SO3 has a negative 1 charge. We know that's not the case because we know SO3 has to have a negative 2 charge. So if that's the case, we had to multiply that charge by 2. We have to do the same thing to our cation, which means lead ends up with a positive 4 charge. So the name of this compound, remember, is lead. We name our cation first. Lead is a type 2 cation, meaning it can have multiple charges. The charge on this version of lead is IV, or 4, and our anion is sulfite. Lead 4 sulfite is the name of our compound. The other way to look at this, if you liked my other method for determining charge just a little bit better, is you know the charge on sulfite. So if you can recognize sulfite as SO3, you know this whole species has a charge of negative 2. There are 2 of them. here. So the total charge contribution for this anion is -4. For every 2 of those, there's 1 lead. So to be equal but opposite, lead would have to have a +4 charge. To me, this is a little bit quicker, but do whatever works for you. Take a minute to do the practice, pause your video, and then come back and we will go over the answers. For the first one, nickel 2 acetate. Nickel has the symbol Ni. The 2, the II in parentheses, means I have a +2 charge. Nickel is type 2, so therefore it can have more than one charge. That's why the parenthesis with the Roman numeral is there. Acetate, C2H3O2 with a -1 charge. Now, this one is no different than the others. You're going to put a base, parentheses around the base of the polyatomic, and then you're going to crisscross. So this becomes Ni, an implied 1 that I don't have to put there, parentheses, C2H3O2, close parentheses with a 2 on the outside. For the next one, iron 3 nitrate. We start by looking at iron, which is Fe, and then that 3 in parentheses tells us that the charge on iron is +3. Nitrite is NO2 with a -1 charge. Now you could see negative or -1, they both mean the same thing. Put parentheses around the base of your polyatomic until you figure out if you need them, and then do your crisscross. We get Fe with an implied 1 that we don't have to include, parentheses, NO2, close parentheses, with a 3 on the outside. ZnCO3, so we should be able to recognize Zn as zinc. Remember, zinc is one of those that we identified as type 1. It always has the same type of charge, and that type of charge doesn't even matter here because we don't have to put it in parentheses in Roman numerals because it's understood that zinc always has the same charge. So you should be able to recognize CO3 as a polyatomic, and this is carbonate. So the name of this compound is zinc carbonate. CuCN, we should be able to recognize our cation as copper. Copper is type 2, so it will have multiple charges. So we need to figure out what that charge is going to be. We should be able to recognize this as another polyatomic. You should be able to get a clue by the 2 capital letters here that it has more than one atom for the anion. So this is cyanide, and the charge on cyanide is -1. Notice copper and cyanide exist in a 1-to-1 ratio. There's one of each of them in this formula. So therefore, copper's charge has to be equal but opposite. Copper has to have a charge of +1. So this becomes copper 1 cyanide. Hydrogen phosphate. Hydrogen has a +1 charge. Phosphate, the formula is going to be PO4 with a 3- charge. So we do our crisscross, put parentheses around the base of our polyatomic, unless you can see that already that we don't need them, and that the formula of hydrogen phosphate is going to be H3PO4. And the last one, aluminum phosphate. The symbol for aluminum is Al. You can see that it is a type 1 cation. So it has a +3 charge because we were able to label its column. Phosphite is PO3 with a -3 charge. -3, 3 negative. There is a proper way to do it, but I don't care which way you write it when you're showing me your work. So we can see aluminum has a +3, phosphite has a -3. So this puts them in a 1-to-1 ratio. For every 3 aluminum, I have 3 phosphate. So I can simplify that just by writing AlPO3. For our last section of this chapter, it's relatively short, and what we're really looking at here is what happens when hydrogen is our cation. So our first aim is to learn how the anion composition determines an acid's name. And the second is just to learn some names for common acids. So the first thing we have to talk about is really what is an acid. So an acid is anything that contains hydrogen as a cation. So when you see hydrogen in a formula as the first element, that should be a clue to you to name that compound as an acid. So when hydrogen is your cation, name the compound as an acid. So acids have their own set of naming rules. When your anion does not contain oxygen, so this means when it's not a polyatomic, when it is just an element that we can find off of the periodic table, this is the first class of acid naming. You're going to use the prefix hydro. You're going to use the root of the anion, and you're going to use the suffix ic acid. So as an example, if I have something like HCl, notice this does not contain oxygen. So I'm going to use the following rules. The prefix hydro, I'm going to use the root of the anion, chlorine, the root is chlor, and I'm going to add the suffix ic acid at the end. It's not complete if I leave off the actual part that says acid. So the full name of this compound would be hydrochloric acid. For the next example, if I have something like HBr, again, my anion does not contain oxygen. Hydro in the beginning, I use the root of the anion, and the ending ic acid. The second type is when the anion contains oxygen. So this is going to be polyatomics that you're looking at. Two basic rules. Ate becomes ic, ite becomes us. So when the polyatomic ends in ate, it becomes ic acid. When the polyatomic ends in ite, it becomes us acid. H2SO4. So you need to be able to recognize your polyatomic. So again, we isolate the SO4 part of this polyatomic. Sulfate becomes sulfuric acid. Notice that if an acid has a polyatomic as an anion, we do not put hydro in the beginning. Hydro is only when our anion comes directly from the periodic table and just that element. H3PO4, we should be able to recognize PO4 as the base for phosphate. Phosphate becomes phosphoric acid. In this case, the root of the anion is phosphor, which comes from phosphorus. H3PO3 is phosphite. That becomes phosphorus acid. Ate becomes ic, ite becomes us. So just a quick look at all of the different types that we're looking at. Phosphate becomes phosphoric acid. Phosphite, phosphorus acid. So this one, if you notice on your sheet, can be written a couple of different ways, but you should be able to recognize this as acetate. Ate becomes ic. This becomes acetic acid. HClO3. ClO3 is chlorate. Ate becomes ic. This becomes chloric acid. HNO3, you should recognize the NO3 as nitrate. Ate becomes ic. This becomes nitric acid. HNO2, one less oxygen, is nitrite. Ite to us, nitrite becomes nitrous acid. H2SO4, you should recognize the SO4 as sulfate. Ate to ic, sulfate becomes sulfuric acid. H2SO3, this is sulfite. Ite to us, this becomes sulfurous acid. So we have to be a little bit careful here because we're not actually cutting anything off of the name sulfuric or sulfurous. And this just comes with practice, getting to see all of the different types and the different examples.